Okay, so in this video, I'm going to be talking about Cayley diagrams and quotient groups. So first of all, I'm going to do an example where we look at S3 modulo the subgroup generated by R. And at first, you might not understand what this R is standing for until you remember that S3 is isomorphic to D3, the dihedral group on the triangle. So then once you think about it like that, R is going to be standing in for one of those rotations. So we normally write the dihedral group with a diagram that looks, like this. Kind of have this internal and external diagram. But when we write the Cayley diagram for quotient groups, what we want to do is organize the diagram according to the subgroup that we're modding out by. So we want to organize it in this case by the R, the normal subgroup. So we're going to organize the diagram by R. So what does this mean? Well, this essentially means that we want to clump the R's together, and then we want to clump or when I say R's together, we want to clump, this is a very technical word, the subgroup R together and clump elements of the cosets together. Okay, so since the order of D3 is equal to 6 and the order of R is equal to 3, we're only going to have two cosets. So in this case, we're only going to have like two of these clumps to worry about. Okay, so I'm going to start out, I usually start by writing the elements out in a row and then think about how I can connect them. So I have R and I have R squared. And actually I should have probably started by writing E over here. Usually I write that in the upper left-hand corner. And we'll usually use one of our generating arrows to be that guy, I think in this case. And then when we apply it again, we'll get back there. Okay, and this is for dealing with the dihedral group. I think another obvious generator is going to be the flip F. So we'll let the red one be the flip. And this will lead us to a different coset. So it's going to lead us to RF if we read from left to right, and then R squared F. Okay. And this is almost what I want to do. But then notice that when I draw my R arrows, the flip F can't go nicely like this, right? So this is normally how I would start out writing my diagram, but F does not just go to RF, right? Because this actually goes, well, let me write this out a little bit better. So this arrow should actually go to FR, and FR is equal to R squared F. So this arrow should actually go all the way over there. And since I'm trying to organize my diagram by R, I'm going to want to line these up more nicely. That is, I'm going to line up my cosets a little bit more nicely according to R. Now this is getting maybe a little bit into the weeds. In this case, it doesn't really matter that much exactly how I'm lining it up, but in some cases it can matter. So I'm going to really pay attention to lining everything up according to R first, instead of just going according to those flips. So once I have one element of the coset in place, now I'm going to go back again, and I'm going to pay attention to generating in R. Okay, so this is actually going to go to F, then R. And then this one will go to F, then R squared. Okay, and then now I can return to my flips, and I actually get a cross flip now instead of that straight up and down flip. Okay, so now I've organized, oh, and I need to remember my other, I have one more R arrow left, and it will just go back like that. So you can check that this is organized correctly. Okay, so now I have this diagram organized by R. It looks a lot different than my normal dihedral diagram, but you can see really clearly that I have my diagram organized by R, the subgroup generated by R. So I have the subgroup generated by R here, and then I have its single non-trivial coset in the second row. And this is really where a lot of the work comes in. Now, in order to see S3 quotient R, I can clearly see the cosets in each row. And further, every single coset has arrows that lead from the coset to the other. That is the red arrows lead from the first coset to the second coset. There are no red arrows that go within cosets in this case. So I can shade the elements of one coset and shade the elements of the other coset together. Okay, and here I'm identifying the cosets. And then S3 modulo R will just be what happens when I identify all of those nodes together. So I have a single node, R, and I have a single node, F, R. And then they're going to be connected by a line that represents the flip. Okay, and then this is my Cayley diagram for the quotient group. Okay, and so we see this, like what we refer to as collapsing of the group into itself, where we've put all of the cosets together. Now, what allows this to occur? It's really what we think of as this like unambiguous arrowing from one coset to another, and it's maybe not as obvious when we only have two cosets. So let's look at a bigger example. Now maybe I'll actually do an infinite example just to illustrate that we can go bigger. And let's do one that we definitely know the answer for, Z3. So this is equivalent to Z modulo the subgroup generated by 3. And so in this case, if I'm drawing out the normal Cayley diagram, normally I would just draw 1, 2, 3, and so on. And then I could go to 0, of course, and then the negative numbers as well. Okay, I'm not going to do that this time because I want to organize it by the subgroup generated by 3. So what I'm going to do is again try to line up my my subgroup elements. So I'm going to start out by drawing those out. So 0, 3, 6, 9, 12, and then I never leave enough space for the negatives, but they should be there as well. Okay. And then I'm going to, well, they can't be connected right away because there's only one generator and they rely on the other elements. So I'm going to have to write out those elements as well. So another coset is the things that are one more. And then the third coset are the things that are two more. Okay. And so in order to see the connection between these, I'm going to have to write it like this. I haven't drawn bubbles around the elements either. Kind of illustrate that this pattern continues on. Oh, and actually, I want this last arrow to come up from the bottom to illustrate that I can keep doing this. So for the negative side, it will go -1, -2. And then this red arrow keeps representing +1 all the way along. Okay, so in the top row, I have the subgroup generated by 3. In the second row, I have the subgroup 3 plus 1. This is a coset. Instead of writing like 1 times 3, I'm just writing the plus because we know that this is our operation. And then in the third line, this is 3 plus 2. And so since we have these all organized according to the cosets, I can just shade them in because we're going to collapse each one into a single element. Okay, so collapsing each of these, we get 3, 3 plus 1, 3 plus 2, and they're each connected according to the +1 action. And then this is the Cayley diagram for Z modulo 3. Okay, and notice that it's still like a cyclic group. It's still a cyclic group of order 3. It's just lined up a little bit differently than what we would often see. So this is the way that we construct Cayley diagrams according to quotient groups. And one of the things to notice here is that it's really important that everything is normal. That is, all of the arrows in our lines are going to the next coset in a predictable way. So all of the cosets can be lined up, and then the arrows point out of the cosets and into the cosets elements in the same way, so that when we collapse, we know exactly where to draw these arrows. Okay, sometimes you don't really know where to draw those arrows, and then that's when you know you do not have a normal subgroup. Let me know if it would be helpful to make a video where I show you when you can't collapse something, because yeah, that's when you really run into trouble.